So this is kinetic molecular theory. This is going to lead us into the gas laws. All right, when we talk about kinetic molecular theory and when we talk about the gas laws, we are going to consider what's called an ideal gas. And that's just like when everything goes to expectations, right? Everything behaves how it's supposed to behave. We're going to act like some of the real world problems we have don't exist here. Okay, so an ideal gas, it fits all of the assumptions. Okay, so we're going to go through these 5 assumptions. Is that gases consist of a large number of tiny particles that are far apart relative to their size. So we know that gas particles are so tiny that we can't see them, right? But really, in a gas, most of that space is just empty, right? Most of the space is particles that are far apart, and they're just in constant motion. So a lot of the volume that we consider of a gas is really just empty space, but it's particles in motion. What do you think, how do you think gas particles move? In a straight line, in a curved line, in random lines, where do we think? Okay, yes, kind of random, but they will move in a straight line until what happens? A gas particle will just move in a straight line until what? Until it hits something. What are the possibilities of things it could hit? Boys, what are possibilities of things that gas particles could hit? The wall, a solid, another gas particle, right? They're going to collide. They won't mix, they'll just collide and they'll bounce apart. So collisions between gas particles and the container wall are considered elastic collisions. We're going to dive into what that means here in just a minute, but it's considered to be an elastic collisions. They are in constant, rapid, and random motion that puts them moving in a straight line. So these 2 assumptions of kinetic molecular theory are really based in physics. Okay, Newton's first law, Newton's law of inertia, says objects in motion stay in motion. Objects in motion stay in motion. Okay, and there's more to that, but objects in motion stay in motion. So objects, gas particles here, will continue in a straight line path until something makes them change. That could be that they collide with another particle and then they go out from there. It could be that they collide with the wall of the container. But whenever they collide, it is considered an elastic collision. I want to think about what an elastic collision looks like. Have you guys ever played pool or billiards, right, on a pool table? What's supposed to happen? Okay, so I hit the white ball, the cue ball, and I hit another one. What's supposed to happen to that cue ball after I hit it?
Depends on what spin you got on it.
Okay, let's just say it's real straightforward. It's supposed to stop. That would be considered a perfectly elastic collision. So let's see what that looks like. If I had a cue ball that is rolling in motion to hit a different pool ball, right? Once that cue ball hits the red ball, what's the red ball going to do? It's going to go. And it's going to go at the same speed of the cue ball. So let's say the cue ball was moving 3 meters per second. Then this guy was at 0. Now he would be moving 3 meters per second, and the cue ball would come to rest, right? In an elastic collision like this, they essentially just swap speeds, right? They swap speeds. If they weigh the same, they would swap speeds. So if this one was at rest and this one was moving, then it would just swap, right? And back and forth. That would be a perfectly elastic collision. We see it demonstrated a lot in those little, those little desk ornaments called Newton's cradle with the little silver balls that go back and forth, right? Those are examples of perfectly elastic collision. You're seeing the energy transfer from one object to the next. And so that's what happens in these collisions. I'm moving at some speed, I hit something, now I have to pop back, right? Or I have to go a different direction, or I have to take on whatever speed of the particle that hit me, okay? That's essentially what happens in an elastic collision. Oops. All right, a couple last things here. It says the forces of attraction, there are none of them. No forces of attraction between gas particles. So in the real world, we see some little attractions happening. But when we are talking in our scenarios, we're assuming everything is perfect, right? These little nuisances we can ignore. So we're going to assume that gas particles can float around as they're supposed to without having that attractive force that might slow down our objects, right? We're assuming they're just going to go and collide. And then the last part is that temperature of gas depends on the kinetic energy of the particles. So we need to think of temperature or heat as a type of energy. As I increase the temperature, what happens to the particles? Do you think they move faster or slower? Faster. They move faster, right? As I increase the temperature, they have more energy, which puts them into motion faster. As I cool down my system, what happens to that energy? Right, the energy gets removed, right? I'm removing energy from the system, making it colder, which means my object slowed down, right? We move slower in the cold, faster in the heat, okay? All right, I'm going to get rid of this. Okay, so let's move into our actual section about gas laws. Now we're going to put them into mathematical scenarios, okay? Gas laws. This is fun stuff. So let's introduce some units and some equations for gas laws. Gas laws has a set of conditions. Guys, I don't want to talk over you. Gas laws has a set of conditions called standard, temperature, and pressure. Standard, temperature, and pressure. This is the acronym STP. It stands for standard, temperature, and pressure. It is a set of conditions. Okay, a set of conditions. So if I say something is happening at STP, it means it has a certain temperature and a certain pressure, and I'll get to those in just a minute. Okay, but if you say something happens at STP, it is a standard set of conditions. The units for those are Kelvin is the temperature unit. Temperature unit is Kelvin. Have we heard of Kelvin before?
Yep.
Yeah.
Maybe. Do you know how to get from Celsius to Kelvin? Right down here. If I have my temperature in Celsius, I'm going to add 273 to get to Kelvin. All right, and this is what we're going to have to use in these gas laws. Okay, we have to convert to Kelvin. So maybe put this on your equation sheet. Okay, you might write Kelvin equals degrees Celsius plus 273. Okay, so this should go on your equation sheet. This other equation tells us how to go from Fahrenheit to Celsius. Okay, so this might look like this. Celsius equals 5/9 times your Fahrenheit temperature minus 32. Right, that could go on your equation sheet as well. We don't have to do this calculation very often because in science, we use either Celsius or Kelvin. We don't use Fahrenheit very often. So keep this one like in your back pocket if you need it, but we won't use it super often. Okay, so introducing STP. We know the units for temperature are Kelvin. We know how to convert a couple of those things. So tell me, if I said my temperature was 100 degrees Celsius, what's my temperature in Kelvin? .373 Kelvin. Good. We don't put a degrees Kelvin. It's just called Kelvin. I don't know why. But it's not a degrees. We just put the capital K. Okay. Here's our pressure units. Pressure units. There's a lot of them. But the most common way we measure pressure is something called atmospheres. Okay. We measure pressure in atmospheres. Measure pressure in atmospheres. There are a lot of different ways that in just our everyday life we measure pressure, but scientifically we need to measure in what's called atmospheres. So we're going to keep each of these as conversions that we could do. These can go on your equation sheet if you want them to. Okay, so they can go on your equation sheet if you want to. These 4 things. Because we're going to have to do some conversions. Okay. Yeah, PSI looks familiar. Where do we see PSI?
Air pressure.
Air pressure, typically in tires, right? It stands for pounds per square inch. Pounds per square inch. Okay. So atmospheres is just another way for us to measure pressure. Let's talk about a couple of the other ones. mmHg. mmHg. Let's see what that stands for. It's a unit of pressure, but it stands for millimeters of...
Hydrogen grams.
Nope. Millimeters of mercury. Millimeters of mercury. Hg is mercury. So millimeters of mercury. This is how a barometer is measured. Have you heard the term barometer before? Barometers measure atmospheric pressure. So they might hang on the wall, like weather stations and stuff. And it's literally just a column of mercury, similar to a thermometer. And it just fluctuates based on the pressure in the room. Okay, or the pressure outside. So that millimeters of mercury literally tells us just how tall that column of mercury is. The greater atmospheric pressure would cause that column of mercury to extend, and smaller amounts of atmospheric pressure would cause that to go down. Right, so we just literally measure how tall that column of mercury is. That one's kind of interesting. The other two are more just scientific ones. We don't see them in everyday life. Okay. But we will have to convert these. So let's do a couple of these. Write these like in the margins or off to the side here. If I wanted to convert, let's say that I was given a value of 22.6 psi, and I wanted it to be measured in atmospheres, how would I convert that? Okay, how would I convert that? I'm going to do just a real simple T-chart. I'll start with what I know. 22.6 psi, and I'll go psi to atmospheres. And so we're going to go 1 atmosphere equals 14.7 psi. So I would divide by 14.7. That's as intense as the chart gets. This is just a simple conversion, like going from centimeters to meters or inches to feet or whatever. We're doing the same types of conversions here. Okay, so 22.6. Oops. Gives me 1.54 atmospheres. Do we see how we could convert that? Yes? No?
Yes.
Okay. Let's try one more here. What if I was given 712 torr and I wanted that value in kPa, kilopascals? Do I know how many torrs are in 1 kilopascal?
Yeah.
Or how many kilopascals are in 1 torr?
Oh, no.
I don't. So what's my middleman here?
ATMs.
Yep, atmospheres. So this almost works like moles. I'm just going to go 712 torr to atmospheres, and then atmospheres to kPa. Right? We see how we work that through. Atmospheres is our middleman. We can convert everything to and from atmospheres. But I just don't know how many kilopascals are in a torr. Don't know how many torrs are in a kilopascal. So I'll put in 760 is to 1 atmosphere. 1 atmosphere is to 101 point. Let's keep that at 101.3. We can drop those other couple decimal places there. It's not the end of the world. So 712 times 101.3 divided by 760 gives me about 94.9 kilopascals. Are we comfortable with being able to convert those units?
Yes.
Most of the time, we're just going to have to go 2 atmospheres because that's what we want to go in our equations all the time. Okay? Okay, so we've introduced pressure and temperature. Now let's figure out what are the conditions for STP. Okay, STP is standard temperature and pressure. Okay, and I'm actually going to mix and match these a little differently. So I kind of want you to rewrite them. They all are the same, but here's what I want. I want you to know that STP is 1 atmosphere of pressure and 273 Kelvin. Okay, it was kind of mixing and matching my units, but what I really want is this set of units. Okay, I want you to know that STP means that the pressure is equal to 1 atmosphere and the temperature is equal to 273 Kelvin. Okay, so when a problem tells you this gas is existing at STP, we know that the pressure is 1 and the temperature is 273. And then we'll be able to know what happens in its fluctuating from there. Okay, so STP means that pressure is 1 atmosphere and temperature is 273 Kelvin. 273 Kelvin is the same as 0 degrees Celsius, right? But we don't use Celsius as often. So I want to keep it in those units. All right, so today that told us STP means we have 1 atmosphere of pressure and 273 Kelvin. You might want to write that on your equation sheet, okay? If I was going to write it on my equation sheet, I would say STP, pressure equals 1 atmosphere, temperature equals 273 Kelvin, right? STP is a set of conditions, standard temperature and pressure. Okay, so if I was going to put that on my equation sheet, that's how I'd write it, right? STP means that I have a pressure of 1 and a temperature of 273. So let's go back to our problem here. Talk about 3 different gas laws called Boyles, Charles, and Gay-Lussac's law. Let's introduce Boyles' law first, okay? Boyles' law, it tells us about the relationship between pressure and volume. Okay, Boyles' law tells us the relationship between pressure and volume. And it says they are inversely related. They are inversely related. So that means when one of them goes up, the other thing goes down, right? If I have something and I increase the volume, the pressure would decrease. Okay. Envision a balloon. I want you to envision a balloon. Okay, think about the particles moving inside the balloon. So we've got a balloon that's tied up. Are we envisioning that? Yes. Now we take the balloon and squeeze it so that it's half the size, right? We squeeze it so that it's half the size. What did we do to the volume?
Shrunk it.
We decreased the volume. So those particles moving inside, do they have a greater pressure or a lower pressure? Greater. Okay, let's think about what pressure means. Pressure is essentially how often those particles will collide with the sides of the container. So the more often they collide with the sides of the container, the greater the pressure. So if I'm decreasing the volume by squeezing that balloon, those particles are going to run into the sides of the container way more often. We agree with that? Can we visualize that? So that pressure is going to increase, okay? So here is our equation for Boyles' law. P1V1 equals P2 V2. We need to write this on our equation sheet. This is Boyles' law. P1V1 equals P2 V2. The 1 and the 2 just mean like initial and final, right? Or start and finish. But when we see this, we know we're going to have a change happening, right? There's going to be a change in pressure or a change in volume. So P1V1 equals P2 V2. We like for the units of these, pressure to be atmospheres and volume to be, what's capital L stand for? It's a volume unit, it's liters. So we like for them to be in atmospheres and liters, but the reality is, as long as the pressure units are the same on both sides, and the volume units are the same on both sides, then we could keep it. Okay, so if pressure was in PSI on both sides, we could keep it that way because the math will work out the same. All right, and if volume was in milliliters on both sides, we could keep it. All right, but that's how it goes. Let's try one. Okay, it says 1 liter of gas at STP is compressed to 473 milliliters. What is the final pressure? Okay, so I want us to start listing out what we know. Okay, 1 liter of gas. What does that represent for us?
The volume.
The volume. And do you think it's initial volume or final volume?
Initial.
Okay, so we might say V1 is equal to 1 liter. It says the gas is at STP. What does that mean the pressure of our gas is? What are the conditions at STP? Go back and look. Right? We said at STP we have a pressure of this and a temperature of this. What are they?
Oh, 1 of 273.
Yep. Pressure is 1 atmosphere and temperature is 273 Kelvin. That's what it tells us, right? We had this slide right back here. It says that our gas is being compressed to this, 473 milliliters. What variable does that represent for us? Is it a pressure unit? Is it a volume unit? Is it a temperature unit? It's volume. And we know, is it initial volume or final volume? I think it's final because our initial volume was 1 liter over here. Okay? And so this is 473 milliliters. And it asks me, what is the final pressure? P2 is my question mark. We're going to write out what we want to know, right? I want to know P2. Does it mention anything here about a temperature change?
Nope.
No, so we really can just ignore temperature because it's not changing our problem at all. So we don't need that temperature. Sometimes we will, but for this one, it doesn't tell us there's a temperature change. Do we see any kind of red flags here? Do those units match? They don't. One's liters and one is milliliters. So we need them to match. Okay, so let's go ahead and convert this one from milliliters to liters. 1 liter is equal to 1,000 milliliters. So we're just dividing that number by 1,000, 0.473 liters. Okay, how comfortable are we with doing that quickly? Going from milliliters to liters. Can we divide by 1,000 and do that relatively quickly?
For that, yeah, but is it only gonna be milliliters?
Typically. Typically. Okay, so if I want to go from milliliters to liters, I just divide by 1,000 real quick. All right, so now I can look at Boyles' law, which we said the equation for Boyles' law is P1V1 equals P2V2. Let's go ahead and plug in our numbers here. P1 was 1 atmosphere. Everything's multiplied here, so V1 is 1 liter equals P2, which we don't know. So we're going to leave that as P2 times V2, which is 0.473. Okay, and this is in liters. If we were following our expectations for Boyles' law, we said if one goes up, the other goes down. So can we expect our pressure to be higher than its starting point or lower than its starting point?
Lower. Higher.
What happened to the volume?
It got lower.
It got lower. Volume went down, so what do we expect the pressure to do?
Higher.
Go up. Okay, so now let's solve the math and see if it works that way. If I want to solve for P2, if I want P2 by itself, what do I need to do mathematically to get P2 by itself? Divide by 0.473 liters, so that's canceled. Divide this side by 0.473 liters. So I'll take 1 divided by 0.473, and I get P2 equal to 2.11. And what unit would go with my pressure variable there?
Liters.
Yep, atmospheres. I know that because that's the unit for pressure, but I also know that's what my initial pressure was measured in. So my final pressure then has to be measured in that unit as well. Try this one on your own, and we'll see how it goes here. We've already looked at the relationship between pressure and volume, and so now we're going to look at the relationship between temperature and volume. Temperature and volume are directly related, which means if one of them goes up, the other one goes up. Okay? We are under the assumption for Charles' law that we have constant pressure. Okay? The pressure in my vessel is staying constant. So if I increase the volume, that must mean that my temperature had to increase so that my particles could move faster and push that volume out. Okay, if my objects get colder, they're not going to move as much, so that volume will shrink down, right? They're not going to be hitting the walls of the container as often, so they're going to be so it's going to be shrinking down. Okay, so these two are directly related. So here is our equation for Charles' law. V1 over T1 equals V2 over T2. Okay, so that one needs to go on your equation sheet as well. V1 over T1 equals V2 over T2. Tell me, what unit do you think the temperature should be in here? Celsius or Kelvin? Kelvin. That's why we practiced converting to Kelvin. Because here's the example I gave a little bit ago. If I have the temperature 0 degrees Celsius, can I ever take something divided by 0?
Nope.
I can't do it. It messes up my whole math problem. So it won't work. So we have to have our temperature in Kelvin. That's a must for these ones. Okay, so let's go ahead and start one here. Okay, if I have 67 liters of helium in a balloon at 28 degrees Celsius, and I increase the temperature to 47 degrees Celsius, what will the final volume of my balloon be? So let's write out what we know. Okay, 67 liters. Is that temperature, pressure, or volume? Volume. So that has to be V1. 67 liters. Does it matter to us that it's helium?
Nope.
It does not. It's not going to change the way we solve anything. At 28 degrees Celsius, is that T1 or T2? 1. 28 degrees Celsius. Do I want to keep it in Celsius? No. How do I convert to Kelvin? Plus 273. Okay, so let's go ahead and do that. 28 plus 273. That's how we convert. Instead of having to do a T-chart, it's just an addition problem. So this gives me 301 Kelvin. All right, let's keep moving through our problem. We've used both of those. I increased the temperature to 47, so that must be T2. 47 degrees Celsius. We're going to add 273 to that. Gives me 320 Kelvin. And what will the final volume be? So that means I must be looking for V2. I think it's really important that we put that question mark, right? That we know exactly what variable we're looking for. Okay, so we'll come put it in our equation here. V1 over T1 equals V2 over T2. Let's plug in the numbers that we know. V1 is 67 liters over T1 is 301 Kelvin. V2 is what I'm solving for. And T2 is 320 Kelvin. Any ideas on how we can solve these questions like this? That's kind of like a proportion like that. Bingo. Cross, multiply, and divide. Cross, multiply. Have you heard that term before? Cross, multiply, and divide. So if I want to solve for this guy, I'm going to cross multiply, then divide. I don't know the notation your math teachers use when they do that, but does that look similar to what they're telling you to do? Cross multiply and divide. So I'll take 320 times 67 divided by 301. And I get V2 equal to what? Go ahead and plug that into your calculator, see what we get.
71.2.
Good. 71.2. What would my unit be for that since it's a volume? Liters. I could go back and look. My initial volume was measured in liters, so that's what my final volume needs to be measured in as well. Do you feel comfortable manipulating that equation? Okay, that proportion there is just cross multiply and divide. All right.
In Boyles law, if they're giving temperature and a volume.
So Boyles law is just P1 V1 equals P2 V2. So we leave temperature out of that one. I'll show you one later that's got all three things in it, and we'll use that same cross multiply divide. Yep, good question.
So how I would find.
Why don't you try this one on your own? Try this one on your own. This one is asking us for something different, but we're going to use the same type of thing. I have 130 liters of gas at a temperature of 250. If I decrease the volume of the gas to 85 liters, what will the temperature B. So go ahead and write that, what you know. Get your equation set up, and let's see if it comes out correctly. So this one is Gay-Lussac's law. And I've just got one example problem here to do, and it's listed right below here. Okay, it says determine the pressure change when a constant volume of gas, that has to be true in these ones, right? The volume of these containers has to stay constant. At 1 atmosphere, so that has to be P1, is heated from 20 degrees Celsius to 30 degrees Celsius. So do we see some red flags here?
Yes.
I do.
See some.
I see some too.
Them C's should turn into K's.
There we go. We want Celsius to become Kelvin. So we're going to take and add 273 plus 273. So this is 293 and 303. Tell me, what's our prediction for pressure? Is it going to go up or down? Make a prediction here for pressure.
Down, down, down. It's down.
Put your thumb. You think pressure's going to go up or down? I'm only seeing like 3 predictions. Take a guess. No one cares. Up or down? Right? They are directly related, which means if one goes up, the other one goes up. Okay, so we should be thinking that pressure is going to go up here. Okay, so P1 is 1 atmosphere over T1, 293, equals P2 over T2. So we're going to cross multiply and then divide. So 303 times 1 divided by 293. So pressure becomes 1.03 atmosphere. So did it go up? Did it go up? Mm-hmm. Not by a lot, but it went up. But did temperature go up very much?
No, it did not.
No, it did not, right? Temperature didn't change a lot, so pressure's not going to change a lot. All right?